is Paul Cocal. I'm French. I studied in Paris at the École Supérieure, and now I'm a PhD student working with Edmond Web Library in September 2017. So this slide explains a little bit my exciting life at IPhT. So just remind that the number of my office is 150. So if you want to talk to me, I'll be there, except during the lunch because I really like the cafeteria. So this is a picture of the famous restaurant Les Algorithmes. But of course, eating is not the only thing I do when I'm in the lab. I also work on my PhD. So this is a view of the CMS detector. It's a very complicated stuff with a lot of wires and everything. But maybe an even more complicated stuff is to try to understand what happens when experimentalists collide two nuclei in this detector. So the goal of such experiments is to create the quark-gluon plasma, which is a phase of matter in which quarks and gluons are defined. So it's a quite challenging task to extract the properties of the medium created in this collision from the measured distribution of particles in the final state. So for instance, here you can see the typical event of after lead-lead collisions measured by CMS, and you see that besides the large amount of soft particles around here, there is at this point here a collimated spray of particles, energetic particles that we call a jet, and this jet comes from hard scattering produced at the early stage of the collision. And when this jet is produced inside the medium, inside the plasma, its interaction with the surrounding medium leads to a modification of its structure. And understanding the modification of the structure of the jet when it goes through the plasma is the goal of my PhD. To infer, of course, the main properties of the medium created in EV ions collisions. So I guess that's it. Thank you.
Can you hear me? Is it working? Like this. Okay. So hello, my name is Giuliano, as written there. I'm starting my second year of PhD. I'm essentially in the same group as before. So it's a STIG group. I work with my supervisor, Jean. And I would like to use this couple of minutes just to give you a picture, an image of what this research is about and what we like to do here in IPhT. And so the title, I think, is what I found appropriate for the title of the kind of research that we do, which is anisotropy in what I call the little bang. So the little bang is sort of a man-made small-scale version of the Big Bang. And as Paul explained, in order to achieve this, you need some very built machine, something that can accelerate particles at very, very high energy, and then you need the nuclei. So you accelerate the nuclei, this mesh, and the system that you form there is a sort of fireball represented there, which is essentially what we want to study. It's a region of space which is extremely hot, extremely dense. You can probably think it's potentially the matter that filled the universe something like microseconds after a Big Bang. It's thousands of billions of kelvins. So we want to study, essentially understand what are the main properties of this very exotic state of matter. So for instance, what is the viscosity, what is the equation of state, this kind of stuff. So of course you see that the scale there is the scale of a nucleus. We cannot see that. So these guys will expand, cool down very rapidly, expand very rapidly. And what is here on the right, which also Paul showed, is not an actual cartoon. This is really what we see. So that's, in a sense, is a little bang recorded by the CMS detector at the Large Hadron Collider. So you see it's a very big mess of lots of particles, a lot of energy deposited in the detector. And so as I wrote there, we can only go in one direction. So we can only see what the detector gives us, and to understand what's going on at the very early stage after the collision, we need to do something. So what we like to do, and what we are actually very good at doing, is to do the following, which perhaps will remind you a little bit of the physics, the analysis of the cosmic microwave background, for instance. You take your big mess, a map of where all the particles are after the collision, where all the momenta are, how they are distributed in space, and you start to look at angles, and you look at how things are distributed in angles, how particles are correlated in angles. And what turns out is that when you collide a nuclei, there is something that you not see in standard particle physics and energy physics analysis of proton-proton collisions, for instance, is that you see very strong anisotropies in this distribution. So you cannot see there, of course, but you should do very careful analysis of all angles, where particles are. Oops. Sorry. Is it my fault? Okay, and so just to conclude, so looking at this angular distribution, we find anisotropies, and anisotropies apparently are very sensitive. They tell us a big deal about what was the initial state of this fireball and how it expanded, how it evolved. So this works very well. We can explain a lot of experimental data from CERN, and I hope you find it interesting. If you want to know more, I'm in Office 150. So thank you.
Thank you.
Okay. So, hi everyone. My name is Sebastian Pögel. I'm originally from Germany, where I did both my bachelor and my master at the RWTH Aachen University in Aachen. In France, it's usually called Aix-la-Chapelle. And so my master thesis was on two-Lewis-Higgs mass predictions in general extensions of the standard model. And so starting last week, actually, I am a first-year PhD student now at the IPhT, with David Kosauer being my supervisor. My PhD is funded through the Sage Actors project under a grant of the under Marie Skłodowska-Curie grant. And just to quickly tell you something about what I'm going to be doing. So my PhD will be on the topic of amplitudes. So as you saw yesterday in the presentation of John Joseph Carrasco, there are some very powerful techniques to simplify the calculation of scattering amplitudes. And I will be focusing specifically on applications of these methods to QCD and QCD precision calculations. With the goal of improving the theoretical predictions that are relevant for current experiments, for example, at the LHC, or also future experiments. Yeah, that's all. Thank you.
Hi everyone. My name is Benjamin Aubin. I'm French. I'm a PhD student. I've just started my second year with Zenkas de Borova and Florence Zakala, which is at TNS. That's why I'm at IPhT only half of the week. And my PhD deals with the statistical physics of multi-layer neural networks, which means that I'm doing my PhD in the interface between deep learning and statistical physics. And our goal is to use tools from statistical physics of disordered system, coming from the study of glasses, and in particular the replica cavity method, or Bullish propagation equations, or IMP algorithms. And we'd like to apply it to multi-layer neural networks, in particular deep learning, to try, because this field is so far only empirical and numerical. So we like putting these things together to provide a theory to understand generalization abilities of neural networks. And in this context, I worked on two different projects. The first one is a storage capacity of binary perceptron with symmetric activation functions, which is related to seminal works of Derrida, Gardner, and Meza and Kraut in the 90s. And a more recent work is about the learning abilities of two-layer neural networks. And that's a paper where we showed that there was a very large gap between what we are able to do with an algorithm and what is achievable theoretically. That's it. Thank you.
Thank you.
Does this work? Oh, okay. Okay. Hello, dear friends. I'm a PhD student in IPhT. My name is Kemal Bechiyev, and I came to France from Moscow. And in the Moscow State University, I did my bachelor and my master degree under supervision of Andrei Slavnov. We studied non-abelian gauge fields, and especially infrared behavior and some non-perturbative methods. Here in my PhD, we work together with Grégoire Miskich, and the main domain of our interest is many body quantum physics, and methods in this field are a lot, and few of them are the most famous I can mention. It's beta ansatz and integrability techniques. Other one, it's a conformal field theory approach, and other one, it's a matrix product state, so-called MPS and MPO. And the question that arises in this domain in out of equilibrium physics, it's effects of disorder, for example. One also can study localization of wave function, some transport properties in the system, and entanglement entropy. Okay, that's it. Thank you.
Thank you.
Right, hello, I'm Felix Roy, and as you can see in the scientific slide, I'm doing population dynamics and logical systems. So mainly I thought I was doing fancy math, but now I'm not so sure about it. And so I'm doing this in the supervision of Giulio Biolori, and I'm starting second year right now. And what we're interested in is that we put a bunch of species together into a mathematical model, and we're interested in knowing which one of them are going to be able to survive together and exist somewhat nicely. And in order to study this, we use statistical physics methods and techniques that come from disordered system and also dynamic system. Thanks.
Okay, my name is Stefano Sarò. I'm a second year PhD in Lanca's group, and I come from Italy. I study mathematics in Turin, Then I studied statistical physics across Turin, Milan, Trieste, and Paris. And finally, I studied nanotechnology engineering in Turin. My interests are in disordered systems and their application to inference in high dimension. And in particular, we are interested in looking at the phase diagram on this kind of problems. We have usually like an impossible phase where algorithm cannot perform any well. An easy phase where algorithm can detect a signal in a polynomial time, and then hard phase where it takes exponentially long time to detect the signal. So one of our main goal is to reduce the hard phase as much as we can by finding better algorithms, and this brings into dynamics. This year I studied dynamics to try to push the hard phase as close as possible to the possible one, and this is related also to the energy landscape, and so I'm interested in the role of the energy landscape and understanding the performance of the dynamics of the algorithm. In this sort of problem, we may have some very complicated energy landscapes, and tuning the parameter in our problem, we can trivialize or trivialize meaning that we have very few minima, or we can have a very raw energy landscapes, and this really affects the performance of the algorithm. And this is extremely puzzling because at the moment there are algorithms that are able, in a very naive way, to escape local minima and to find good one, because also we have good and bad minima, and so we want our algorithm to find the good ones, and this is extremely puzzling, and we don't really know in general what is going on in this sort of problems. And that's it. Thank you. Thank you.
Hi, I am Orazio. I am also a PhD student. Now I'm starting the third year, so I'm looking for a postdoc. So have one. Okay, that's an advertisement. So I work with Marco Schiro in Marco's group, which is made up by these people: Stephen, Francesco, a guy which you have seen around in IPhT and here. So now recently Marco moved to Collège de France, so that's why I would be in the lab all the time, but I would come some days. So I did my studies. I started my studies in engineering in Italy, in Padua. I studied mechatronics engineering, but then I got bored and I decided to continue physics. So I studied statistical physics, complex systems in Turin, Trieste, and Paris the last year, and then I started my PhD with Marco. So what is my subject of research is driven dissipative quantum many-body systems. So basically, these are systems in which you stabilize some non-equilibrium states by basically driving a system which has some losses, so you establish some equilibrium which is not the thermal one, and the goal of my PhD is to study the phases of matter which emerge in this kind of systems. So questions are quantum effects in these states, critical phenomena out of equilibrium, and in general, well, other non-equilibrium properties. So, to the question how to recognize me at IPhT, since this is a presentation to get to know each other, well, if you see someone going around with a blue-wheeled skateboard, it's me. Well, actually, there is some degeneracy. There is also Stefano, which just preceded me, which has the same skateboard, so maybe it's not me. And I think that's enough. Thank you.
So I'm Maxence, and I'm a first-year PhD student in IPhT, actually starting at the beginning of October. I'm working in condensed matter theory with Catherine Pepin and on emergence between the phase diagram of heterogeneous superconductor. I will be able to give you more detail in the next IPhT colloquium if I come back. And also I did all my studies in Paris, but I'm actually from the east of France. So I'm happy to share my office with Sebastian, which is from Germany. And it is known for its wine and its Christmas market, so I really encourage you to go in the winter, like in December. Otherwise, I did a lot of canoeing when I was in Atlas, but due to the lack of river in the Paris area, I'm now resorting to bouldering. So if you are planning to go, especially in Massy, I would be happy to join. Thank you.
Hello, okay. Okay, this is good. Hello, my name is Sarah. So, as you can see, my slide is pretty simple. So this is the only slide that I have. At first, as I'm a new PhD starting like 2 weeks ago, I don't really have anything to say about my subject yet. So they told me if you don't make a slide, then we're going to make a slide with just your name on it, and I thought it wasn't pretty enough, so I made one. At least now this is my subject on it. So officially, I'm going to work on exotic superconductivity in graphene. So that's kind of what my supervisor Christina talked about at the end of her talk, which is the bilayer of graphene that some experimentalists worked on this year and found some exotic superconductivity that nobody is really able to understand yet. But I'm also going to work on the polarization of Majoranas, which is also what Christina is working on. So I guess, yeah, that's it.
Thanks to all the students. And now Monica.